Hi, good afternoon. Today we are going to see about electromagnetic induction. Previous class we saw about electric motor principle. In another video I will or lesson we'll discuss about the motor principle, actual parts of it, what is the use of it and so on. Today we'll see what is electromagnetic induction. As the name says, we are going to induce something in an object. Okay. So here we'll just see a demonstration. A north and south, you're familiar with these kind of diagrams by now, I suppose. It's a magnet or magnetic field is created between the north and south, and I have here a conducting wire. Okay. So you need to have a conductor and say a permanent magnet, then you can achieve this result, what we are going to see here. What I'm going to do is this wire, I'll be just moving it across the field. So where is the field here? North to south. South you have, I'm just going to move the wire so that it cuts through the field lines, and it moves past. It's like you're moving the wire through the board. In that case, you observe, if you're doing this in real life, you will observe there is a deflection in this galvanometer. Galvanometer is a sensitive voltmeter or ammeter. So it is going to show a deflection. So what does that mean? There are some charges that are flowing through in the circuit because we don't have, as you see, I've not connected any other power source. You just have a connecting wire and a galvanometer. So what we have done, there is just a movement of the wire. So the movement we can relate it to kinetic energy. The kinetic energy actually gets converted to electrical energy. Now, if you could recollect, this is the reverse process of electric motor principle. Actually, scientists, they were inquisitive to know if the reverse process could be achieved. Yes, they were successful. When they did this kind of experiments, they were able to achieve the flow of electricity without having any energy source or power supply. Okay. Now, what did we use? As I said, we just need to have some magnetic field between the magnets and a conducting wire, and it has to be a complete circuit. Obviously the charges will not flow otherwise, you will only have static electricity otherwise. So if you want to have current electricity, you need to have a complete circuit. All right, now here I'm just mainly focusing on what you need to remember in terms of your examination. Okay, so the first point is, how would you achieve this? So are there any factors or limitations to this in induction of electricity? Yes, there are. What are they? Now here, if you notice, I've kept the wire and the field, they are at right angles to each other, right? If you notice, it's at right angles to each other. But if I move it like at an angle, say if I move the wire at an angle, you will not find the same amount of deflection, which translates into the same amount of current will not be induced or will not be flowing in this wire. So what's the main factor? That, or the maximum current would be flowing only if this, you have to remember, if the wire or the conductor and the magnetic field are at right angles to each other. So that's the key term here. It should be at right angles. So if you notice, or if you get a situation where the wire is moved horizontally, which means, imagine this to be the wire. If I am moving it horizontally along the magnetic field lines, you will notice that there is no deflection at all here. Okay, so perpendicular, if you place or if you move the conductor, you will get maximum current flow. Zero current flow will be there if the conductor is moved parallel to the field. All right, and it will vary between horizontal and vertical movement. I hope that's clear. So that's one point you please have to remember. Now the second term, or if you're asked to explain electromagnetic induction, you must use the word cut through. So this is like another term for right angles. And also an induced EMF or current flows through it. So this is like you're including all the key terms and you're writing or explaining electromagnetic induction appropriately. Now how do you put it in a sentence if they ask you what is electromagnetic induction? It starts from here. If a conductor, all right, cuts through a magnetic field. So I've used the word cuts through the magnetic field. Then there is an induced EMF. There's an induced EMF in the conductor which will allow a current to flow through. That's very simple. As I said, if you remember those key terms, you can put it in a complete sentence and you will get a meaningful definition. All right. Now, we said the current is going to flow through. Now, this is the fourth rule, the hand rule. In the start of the lesson, I told you there are 4 rules that you'll be learning. 2 right hand grip rules, 1 left hand and right hand, Fleming's rule. This is the fourth or the last one, Fleming's right hand rule. You will apply here for what? To identify the direction of the current flow or the induced current flow, right? Now here, those 3 fingers, you know what they stand for, it's the same, there's no difference. Only thing is that you'll be using the right hand grip, Fleming's right hand rule. So this stands for the field, thumb for the movement, and the second finger for the current flow, all right? Now here, imagine if I'm moving it through or into the board. So the thumb indicates the movement of the wire, right? Now this red arrows indicate the field, all right, field. So these 2 are kept at right angles, and open the third finger. I've explained how to use it correctly in the previous video. Please watch that. Now, when I keep it like this, say I'm moving it into the board, the field is like this, and you can see the second finger pointing down. So in this situation, the current flow will be down. You getting it? So Fleming's right hand rule is applied when you have kinetic energy getting converted to electrical energy. To identify the direction of the current flow, we'll be using Fleming's right hand rule, right? A couple of more information. Now, if you reverse the direction of the movement, if you're moving it out, obviously the current will be flowing in the opposite direction, okay? I don't think there will be any confusion on that. Now, if I reverse both, sometimes they ask in board questions that they ask what if both the the movement and the magnetic field direction both are changed. You can apply Fleming's right hand rule and verify it for yourself. If you flip both, then the effect will still be the same, which means if I make this as south and this as north, and if I am moving the wire outside, you will still have the current flowing in the same direction. All right, I hope it's clear. 3 main points. When does current flow through, or when is current induced? It has to cut through the magnetic field. Maximum current flow is at 90 degrees. And then the prediction of the direction of current flow, you use Fleming's right hand rule. All right, I hope it's clear, and see you in another video. Bye.